everyone. My name is Raina Ghazi and I'm the Teacher Development Manager for Macmillan Education International Curriculum. Thank you so much for joining our webinar. Today we have Bob Kibble, who you can see bright and early in the morning in the UK, Scotland, who is our science author and expert, who will be delivering a really engaging and practical session focusing on practical science at home. If you do have any questions, feel free to write them in the questions box and we'll do our best to answer those questions throughout the session. Thank you. Over to Bob.
Hi, thank you, Raina, and a very warm welcome to everyone listening and watching. I'm delighted to be here with you, and I'm delighted you could join me as well. Today, our focus is on practical science to support learners at home, and we are, most of us across the globe, struggling at home these days, and we share the same challenges. So my heart and my thoughts go out to you and your families. We'll see each other at the other side, I'm sure. Now, during this presentation, I will cut off my camera because you don't really want to see me, you want to see the slides. And I'll make an appearance again towards the end where we can share questions and maybe have a chat about some of the issues. So I'm going to disappear now and say, hope you enjoy the presentation and I hope it's valuable to you. Okay, now we can start. Now I'm speaking from this beautiful place in Scotland. The town I live in is called Peebles, and as you can see, it's very much like this today. It's a sunny day, and the River Tweed runs through Peebles, and it's a joyful place to live. I hope one day you'll be able to visit us, and if not, visit Scotland sometime. And I hope also, in the fullness of time, I'll be able to visit you where you live. We're dealing with science today, and I want to start by making a point about what I've seen in schools and at home about interpreting science teaching and learning. I don't know if you recognise this, the idea of making a poster of a famous scientist, or even this. Well, I see this quite often, and I wanted to place this slide up as a warning, because this project work results in the following. It results in children spending hours on the internet or books, lifting information that they don't understand, and then reading it out quite often to an audience. And no one is very wise after the event. So I want to just guard against that. I will not be going down this line in my science talk today. So my word of warning is, if you're tempted to do this and set this as a task for children, I'd say think again. I'm not saying there's no value in doing such research projects. There is some value, of course, in dealing with information, and particularly information technology, but it isn't science. So I'll be looking at different aspects of science today. I want to address two types of children. Firstly, very young children, probably age 6, 7 or 8 years old, who may be with you at home, because their needs and skills and abilities are very different to the older children who may be from 9, 10 up to maybe 13. So I'll be trying to deal with both sets of children today. For the youngsters, excuse me, for the youngsters, we'll be having a look at the joy of finding out and sharing, just exploring some ideas. We don't need to do measurements and deal with too many numbers for very young children, but they can do lots of good science. For the older children, they'll be used to at school to making measurements, and we can help them at home, help them to take measurements, look at patterns from their results. So that's proper experimenting. So we'll deal with exploring and experimenting today. Now, starting off with the younger children, I'm going to take some examples from something I wrote a few years ago called Hickory Dickory Science, which is science ideas based on nursery rhymes. And we'll take that as our starting point today. Well, here's our first very popular rhyme. The story of Humpty Dumpty is well known by most children around the globe in some form or other. And looking at the idea of young children who are very used to singing or saying nursery rhymes, I was thinking, well, can we use this as a springboard for some science? Well, here's a little science experiment that we can do using the Humpty Dumpty idea. You can draw or print some circles or some egg shapes and cut them out. And then cut them into different numbers of pieces. Maybe one egg can be in 3 pieces, one in 4, one in 2. And the challenge is to put Humpty back together again. If you try 3 pieces, you'll find it's harder than 2, and 4 pieces can be really pretty tricky. 5 pieces, well, I don't know whether you'll finish it before bedtime. Remember, don't turn the pieces over, because if one of the pieces gets turned over, you'll be waiting for hours to try and fit it. And to extend this idea, why not draw a face on your oval before cutting it up? And the challenge is, does this make the task easier or harder? Does it take longer to make your Humpty together again, or is it the same time or less? So that's a Humpty Dumpty activity, and all you need is some paper and a pair of scissors. And you could carry on, of course, using 6 or 7 pieces and have a very complex jigsaw puzzle Humpty. But you'll find if you draw a face on the Humpty, or if you mark the pieces in some way, quite often they go together more easily. On to our next challenge. Incy, poor Incy Wincy spider, look at him there, washed out of the drain pipe. But the sun came out and he was okay again. Now, where's the science in this? Well, there is lots of science here. I could take the line of puddles and water, but let's try and look at spiders. Now, if you can find a spider outside, maybe in a flower pot or a flower border, or in the garden or in the woods, try and find a spider and collect him in a little jar. Be very careful. You could observe a spider. If you have a hand lens, or even not, just look very closely. What could you find out about your spider? How many legs? Let's make a drawing of the spider. It's a spider study. And continuing this idea, let's think about spiders' webs. Why don't we make one? You can use drinking straws or twigs or something like I've shown in the diagram, and a length of string or wool or thread, and children can make their own spider's web. And they might even want to make their own spider, make a model spider. This particular picture I found on the internet, and it's interesting because these spiders, I notice, are linked to balloons and straws. The idea is that I think you blow down the straw, inflate the balloon, let go, and the spider moves. Although I think these spiders will move backwards. Can you see why? So finding materials to make a spider's web or a spider is the end of that part of the project. Another favourite nursery rhyme. Poor Jack and poor Jill tumbling down the hill. Now, is there science here, I think? Yes, I think we can find some science. Let's just make ourselves a small hill. You'll just need something like a shelf or a large book or a table propped up on a couple of other books so that there's a slight incline. And let's think of the words we might use. Language is very important in these learning scenarios. Things that roll or things that slide, roll or slide. Things that are flat, things that are round, things that are neither flat nor round, like a banana. Will they slide or won't they slide? Let's make two groups. One group for things that slide and one things that don't slide. Of course, a ball will be one of the first choices. But what about a cola can? And if you want a real challenge, try a drinking cup like this. Do you think it will slide or roll? Will it roll all the way to the end? If it doesn't, can you say why? Look for shapes. There's the clue. Young children can do this with a little support from a parent or guardian. It's a very easy task. In fact, all of these tasks will work better if someone was just encouraging and listening, and so the child could explain exactly what they're discovering and exploring to someone else. But here's one that is easy to find in the home, something that dissolves. Now, I've chosen here some jelly cubes or some sugar cubes. Either of these, if you can find some, will be great for this experiment. And of course, what we're going to do is pop one into the water, and we're going to look at what happens. We just wait and observe. What do you see happening? I'm not going to tell you, because what happens is something quite unexpected. It's something you probably have never studied closely before. And if you want a challenge to extend, then try warm water with your next piece of sugar. And what do you see happening if the water is warmer? So that's a dissolving experiment. Now this fun with shadows doesn't seem to have a nursery rhyme attached, but it's a favourite of mine. And children in a dark room with a flash torch could easily make shadows and have a lot of fun with shadow puppets and shadow theatres and telling shadow stories. And there's much science here in the idea of the shadow being the place where the light doesn't reach. How can you make your shadows bigger? How can you make them smaller? You might want to make a shadow theatre. You need a big sheet of paper, thin paper, see-through paper or cloth. Maybe your parents could be the audience on the other side, and you are the puppeteer on this side, telling the story. Someone, maybe a friend or sister or brother, holding the torch. And if you move the torch, then the story moves. If you move the cat and the mouse, then the story takes shape. Write your own play and perform it. Okay, enough for very young children. Let's move on to some ideas for older children. Now, in these ideas, I'm going to take an excursion to the world of charts and graphs, just for 5 minutes. Because scientists use charts and graphs to look for relationships. So this second part is about experiments, patterns, and finding out patterns and how things are related. Now, this is a very common chart that you'll find. It's a bar chart. You'll find it in lots of areas of science, mathematics, and different subject areas. We're going to have a look at charts for 5 minutes because this little excursion into the world of charts and graphs is going to be very valuable by the end of this presentation. What does it mean, this chart? Is there a pattern? Well, there's a pattern, things getting bigger or taller. One could even draw a line to show the way the pattern is moving. If I take away the bars, I could replace them with a hill. And walking up a hill is a much more familiar thing for everyone. So let's think about a graph or chart being like a hillside. Here's someone walking up this hill. I wonder what story he will tell once he gets to the top of the hill. He might say something like, oh, that was a steady climb, meaning I wasn't surprised by anything, it was steady all the way. And graphs are rather like that. They can be steady all the way. Or it may be a climb like this. Oh, it's an easy one. It was a very easy starting point and a very easy, oh, it's a descent. Oh, it's a very easy up and down. Or this one, whew, this was a very steep one. So just like hills can tell their stories, so graphs and charts can tell their stories. And part of science education is to learn how to tell the story of a graph or a chart. There's a story here. Something is increasing. Something is decreasing. Something is up and down, up and down, up and down, but actually, over the long period, it's decreasing. So every chart or graph tells a story, and it's being able to tell that story that scientists have that skill. They have that skill in being able to say, well, we got some results, but we can tell the story. So you may have a chart or graph which is a steady rise, like this one, or one that gets a wee bit steeper and then levels off, and that's a different story. Or you could have different shapes of graphs telling you different stories. Think of them like hills, and you can tell the story of the up and the along. I wanted to look at this particular chart for a while because this is a very interesting shape. It's unlikely that you'll find in schools experiments a graph or chart like this, but it's an easy one to talk about. Here we are starting our journey. I wonder what the story will be at the start. Probably, this is a nice easy walk. Oh, this is getting a bit steeper. What's up ahead? Oh, maybe I'll need some ropes to climb this hill. This type of graph is a very interesting shape of graph because we see it sometimes on the news, and we've seen it recently in the last month or so. Do you recognize it? Here it is. This is a chart that I've seen in newspapers and on the news throughout the the challenge we've had over the virus. And it shows the growth of cases and the way that the virus has increased in numbers. And it's just another chart which tells another story. So there's a link between the challenge we have here with the virus and the science of graphs and the stories that we can tell. Let's move on. Back down to school level, and we have a simple task here of growing from seed, a little seedling which grows into a flower, and we're measuring the height of the flower over 4 weeks. It's a sort of challenge that can be done at home, or sometimes it's done at school. And there is a story to be told. Can you see it's linked to our little hill story because there's a gradual increase in the height. And the story that you might tell is something like this, or this. So this is an illustration of how to take a science experiment, produce a graph or chart, and tell a story about the chart. It's a simple pattern and a simple story. So we'll be doing that with some of our experiments now. To summarize our approach, we'll be looking for stories to tell. And the stories will be in this shape. If we change something, then what happens to something else? For example, if we change the weight that we add to an elastic band, what happens to the length of the elastic band? If we change what happens to this? That's the style of our exploring. For example, if we change the water temperature, what happens to the time taken to dissolve? If we change, then what happens? So let's look out for this form of structure when we're looking at our experiments. Okay, experiment number 1. Many homes have fridge magnets or small magnets which can attach to a surface. So if you have one of these or a small magnet, here's the question: will its magnetism reach through paper? Well, what you'll need is your magnet, some paper clips or some safety pins or some tacks or nails, or just something which you have a small pile of metallic objects, and some little sheets of paper. Start by just seeing how strong your magnet is by lifting up the paper clips and counting how many the magnet lifts up. Try it 2 or 3 different times and maybe take an average. On my particular, this is my magnet, and I did this experiment last week. There were 19 paper clips. I placed a piece of paper under the magnet and repeated picking up the paper clips. Now, I'm not going to tell you what the answer was because that's for you to discover. It's a very easy and simple experiment. And here's our question. If we change, we're changing the number of paper sheets, what happens to the number of paper clips collected? If we change, what happens to? Well, here are my results. For no paper sheets, I collected 19 paper clips. And I carried my experiment on, but I'm not going to show you my results because you're going to make your own. And I made a chart. Let's have a look at this chart. Along the horizontal line, sheets of paper, the things I was changing, 1 or 2 or 3 or 0 sheets. What happened? Well, it's the number of paper clips that we were collecting. And I've drawn those numbers vertically on another number line. And it's where our result fits in, which is interesting. Our first result was 0 paper clips, 0 sheets of paper and 19 paper clips. And that's a nice bar that goes there, or a point, but I've chosen to use a bar chart here. My challenge to you is, what shape is your chart? Is there a pattern, and what have you discovered? So that's your first experiment. And here is my good friend Ruben. He's doing this experiment. He started with a magnet, and he did works with a magnet and also a fridge magnet. So he's working away here. Ruben is a youngster, and he's been working with his mummy in the kitchen. And he has a bar chart, just like mine. And he's got his results, and he's written some answers there, and he's telling his story. And yes, his mummy helped him with this. But even at age 6, Ruben could tackle this experiment. So if you're aged 8, 9, 10, 11 or 12, you'll easily be able to do this, probably without too much help. On to experiment number 2. We're looking for another relationship. Can you see what I've done here? The spaghetti is held. I've put mine on a cup with some sticky tack. And I've just sellotaped a strip of paper onto a box, and you could use a book or a wall so that we can mark the position of the end of the spaghetti. There it is in close-up, and I've marked it 0 because that's the starting position. And notice I put a small blob of blue tack or tack on the end of the spaghetti because I'm going to add some weights onto my spaghetti and I don't want them to slide off. That's our first result. So here's our question again from science. If we change, the weight on the spaghetti, what happens to the amount it bends? So this is our science experiment. We're going to add some weight on the end of the spaghetti. And the weight we're going to add is something like a paperclip or a strip of paper that can be bent and hooked over the end of the spaghetti. Piece of card bent in the middle will also do the job. So if you pull out your paperclip, the last part, so it hooks over the spaghetti, then you'll be able to have one paperclip and you'll find the spaghetti will bend and there's a new position. I labelled this new position 1 because it was one paperclip. With more paperclips, you could add more paperclips and you can continue this experiment on your own. Here I am with 4 paperclips and I've marked the position each time. And that's your experiment. Now, let's make sense of our results. I took my strip of paper, placed it on the table and used a ruler to measure the distance between these marks in millimeters. The first mark was very close to 4 millimeters. Second one was 9 millimeters, and I've shown those results on my table. Of course, the first mark, I've placed the ruler next to 0. So I want you to do this and build up your own table of results. How many paperclips? How much bend? There's my result for 2 paperclips. And here's a chart again, and it's showing the paperclips that we added along the horizontal line and how much bend in millimeters. Notice I've gone up in 2s. And so when it comes to finding a 9 millimeter point, well, we're going to have to realize that 9 is the hidden number between 8 and 10. 8, 9, 10. So just between 8 and 10 is where 9 millimeters will be, and 2 paperclips is just above the number 2. So there is our location for that point, that results point on our chart. I'm not showing you where the 4 millimeter went. You could probably guess where that goes for the 1 paperclip, and then the rest is down to you to discover for your spaghetti. Of course, different lengths of spaghetti and different makes of spaghetti will give different results. This could be an experiment that could last all week. Did you find a pattern? What story does your pattern tell? How about shadows? Shadows are very easy to see on a sunny day. Here is there's a bottle of water and I can measure the length of the shadow on my dining table or outside, which is probably a better place to go if you can find a place where you see a shadow. How long is the shadow? If we wait and change different times of the day, what happens to the length of the shadow? You could make a little results table. There's my first result, 10 o'clock in the morning, 56 centimeters. I've indicated these other times, not because I'm going to necessarily use them, but some people think they have to make 10, 11, 12, 1, 2, 3, have to go out only on the top of the hour. You could go out at any time, but just as long as you record the time that you're out. So if I go out at 10:45, I would write 10:45. You could use a smaller object, a pencil inside. The problem with being inside is that sometimes the shadow of the window frame will get in the way. You'd have to move your pencil and paper to a different place inside the house where you find some sunshine. But if it's on a horizontal surface, the experiment can continue. And here we are with my first result, 56 centimeters at 10 o'clock in the morning. I wonder what will happen during the day. That's for you to find out. Is there a pattern? Over to you. Does your pattern tell a story? Well, if it does, What does the pattern tell us about the sun's position in the sky during the day? Because the sun is the thing that's making our shadows. I leave that to you. Experiment number 4 involves good old friend, the sugar. Now, this is not a sugar cube. This is just grains of sugar, and you'll need a clock or stopwatch, or sometimes your mobile phone will have a stopwatch facility on, or even just any watch with a second hand. What we're going to do is going to add the sugar to the water. We'll stir until the sugar dissolves. And here are some images from my experiment at home. I did this in the kitchen. There's the sugar going into the glass. I'm stirring away. There's still sugar. Can you see it? Still sugar at the bottom. Still a little sugar there. And then it's all dissolved. And I would stop the clock and time how long this took. So that's your challenge for experiment number 4. How long does it take? So what happens to the dissolving time if we change the water temperature? So we're going to change the water temperature, and then we're going to take this measurement several times. Now, to change the water temperature, you may need the help of an adult, because you're going to need a jug of hot water. It doesn't have to be boiling. In fact, try not to have boiling water in this experiment, but hot water. And you can pour hot water into your glass, and that could be one of your experimental results. For hot water, how long does the spoonful of sugar take to dissolve? You could add some cold water to your hot water, half hot and half cold, and then you'll have just warm water, and you repeat the experiment. How long does the sugar take to dissolve? Of course, you could just use cold water, and you could even have water that's been sitting in the refrigerator for a while, and that would be very cold water. So one could have cold, cool, warm, hot. You could have 4 different temperatures. I wonder what happens to the dissolving time. Of course, you should use the same amount of sugar on your spoon, 1 spoonful each time. I did mine, my result with 12 seconds worth of hot water. The hot water and the dissolving time was 12 seconds, as I've shown on the table here. And again, on our chart, I have 4 temperatures. Cold water was kept in the refrigerator. Cool was from the tap. Warm was some cool and some hot, and then hot water from the jug. And my first temperature result is hot water and took 12 seconds. And there it is on my chart. So if you do this at home, you'll be able to get your own hot water result and then change the water temperature and find what happens to the dissolving time. And the question is there a pattern? And is there a story to be told of what's happening to the sugar? Experiment number 5 is another rolling experiment, but this time it's a rolling experiment with measurements. And you'll need a little sloping piece of wood or some sort of slope, and you can mark on the slope. I've stuck a piece of paper on mine with 5 centimetre markings. I call these the start heights. The start height, just to give us places for the ball to start rolling from. And there's a photograph of my experiment in my living room, rolling along a carpet. And I found that with my box of tissues, the slope was just right for the ball to roll not too far down the carpet, no more than about 2 meters. Certainly distances I could measure. Different start heights. So you don't need too much for this experiment, but you do need a little bit of space, something to measure with, and a slope and a ball. So if we change the start height, what happens to the rolling distance? there are some measurements to be made. I tried my ball from 25 centimetres start height, and it rolled 71 centimetres. And that was my first result. And there it is on my chart, my graph, the chart of results, table of results. And there it is, these two measurements. The 25 centimetres start height was along that line, and along this line was the 71 centimetres, how far it rolled, and that's my point on the chart. And by changing the start height, I'll build up different places for rolling the ball. So that was my point. And can you find a pattern for your results? Can you tell the science story for the rolling ball? What happens to the rolling distance as we change the start height? Okay, so I'm just going to close down with a reminder of what's happened today. We've had a look at how to explore simple science, yes, making observations and experiencing new things, keeping our eyes and ears open, and just finding the joy of finding out about spiders, finding out about simple things that roll, and having maybe a context of nursery rhymes to hang our science upon. And of course, that's quite different really to the slightly more demanding science, which looks at charts and graphs and patterns, which involves measuring, and we looked at that for older children. So we have nursery rhyme context followed by a science storytelling context. And I hope you'll find out of those 10 different types of experiments enough material there for you to help your children. You will need to help them, and you'll need to be there yourselves just to start them off, but certainly towards the end, once they've finished, you are the audience to which they offer their results. So being an interested listener at the end is a very important part, a very important role for you to play at the end of your science activity. There are contacts here for you, and this will be on your PowerPoint slides when it goes up on YouTube, I believe, and Rainer will explain that. But I will say at this stage, thank you very much for listening. I've enjoyed explaining some science to you. I've enjoyed doing my own science experiments at home because these have all been done in my home. And I enjoy, hopefully look forward to speaking to you again and have fun with your science at home. Thank you very much.
Thank you so much, Bob, for your really engaging and hands-on science activities. We'll just wait to have some questions if anyone has any. But in the meantime, let me just mention, as Bob also mentioned about some of our links, a few people have written some comments about where they can obtain the presentation. So the presentation will be provided as a PDF to you via email, hopefully within a week or just over a week, along with your CPD certificates as well. The webinar recording itself will be available on our webinar YouTube page, as you can see here, hopefully within the next few days. Please do also go to our home learning content page, where you will find a lot of our home resources that you can try with students and children during this quarantine period for maths, literacy and science. Also do follow us on social media, because we always have a lot of content on there and updated information that you can follow as well. So I'll pass it over to Bob just for a few questions, I think there are.
Okay. Someone's mentioning space science. It's a dry topic. I've not tackled space science, and although I am an amateur astronomer and I've done a lot of science teaching in space science, lots of things you can do. Of course, space science can be very, very dry, and there's a lot of just bookwork available, but I would really try and encourage you to get children to look at the night sky. Oh, certainly the sunshine and shadows activity is a space science activity for the daytime, of course, And there are other shadows and sunshine tasks you can do with making a clinometer and following the altitude of the sun. You can also, of course, early in the evening, look outside and see some of the bright planets around if you find there's one. There's Venus at the moment, which is absolutely stunning and is worth looking at. So to actually look at a real planet, look at the moon when you find it, sketch the shape of the moon over a period of several days, try and find, if you have binoculars, try and find some details on the shape of the shading of the moon. So try and make your astronomy project as practical as possible. Even model making can be very useful, and also some science fiction, telling stories of trips to different planets, and even writing a postcard back from a planet. I've seen that as an activity that's been done. Someone said he's met me as well. So, hi, Dr. Singh. Nice to see that you're listening in. There's some activities for teaching sound. Can I kindly suggest activities? Soma Saharoy. Thanks, Soma Saharoy. Quickly thinking of activities for teaching about sound. Well, it does depend on what you want to teach. But there's no shortage of sound in our lives, from the radio or from little musical instruments or tapping of objects in the home. So there are different types of sound, and we can try sound, whether we can hear them next door or outside, or can we put something which is like an alarm clock in a box? Close the box, can we still hear it? Can we cover the alarm clock with different materials? Which material deadens the sound most? Oh, we can do different things around the house with sound. Cup telephones, someone's mentioned. Yes, jolly good. They're great fun. A piece of string and two plastic or paper cups, and you can talk to each other. And there's a task with sound traveling through strings. One of the experiments I've used in Max Science has been the coat hanger attached to two strings, and one goes in each ear. And if you don't know what I'm talking about, you'll have to look at Max Science for that one. Someone's asked me, Anis Farouk has asked me about environmental science during this quarantine period. Well, the environment's a huge subject, isn't it? But hey, have a look at the things that you've got at the home, things that are written on packets. Which things are recyclable? Which things aren't? Can we group them? What about friendly packaging, recycle-friendly packaging? We can have a look at different types of packaging and the things that we throw away and discard, and can we sort them into different types of material? So sorting material is an environmental issue. Then I think you can have certainly looking through windows, things like atmosphere cloud patterns, cloud cover, having a look at newspapers or television or reports online of weather maps with charts. You can make your own weather map with your own symbols for sun, for rain, for lightning, for thunder, for snow, and you can tell your own weather stories for different times of the year. And you could photograph those stories. You could do them, at this time of the year, but pretend you're dealing with winter, pretend you're dealing with springtime. What would your weather map be if you were giving a weather forecast or a weather report? So there's quick things that come to mind. There are lots more that if I had time to think about it, I'm sure I'll be able to tell. Can you show me again the spider hunt activity in the spider web, please? Well, I think, Rainer, all of these slides will be on YouTube, won't they?
Yes, so the slides themselves will be on YouTube. So, no, sorry, the webinar recording will be on YouTube. So if you do want to have a look through, sort of going at your own pace through Bob's presentation, then of course you can watch this on our YouTube page, which is here, Macmillan Education International Curriculum.
I would certainly advise that, because I've gone through these slides pretty quickly, I realise, and my apologies for taking a short time, but I've probably spoke too quickly. So I would certainly say that before you embark on these experiments with children, have a look at them again on your own and use some of the slides with your children, because the slides can explain a lot about particularly how to make a graph and where the numbers go. How do you turn the numbers into a point on a chart or a graph? I think I've written this presentation for it to be used with children, not just on this webinar. So someone has said these are experiments that they want to show their children today. Well, not all of them today, but you can, of course, show your children some of these experiments over the next 2 weeks. I wouldn't try and cram all the experiments into a day or two. I would let them last over a period of time, because some of the results need to be digested and explained, and the materials need to be gathered together. And of course, there are other subjects to be studied and other things for children to do, of course. So a little bit of science every now and then is what I would advise.
Just leave it as maybe one more question, Bob, and then we can I think there's a question from Nisha here, how to teach line of best fit in stage 5, which is a bit challenging for lower achievement students. Is there any way to teach this in a more simplified way?
Line of best fit. Well, I think it's a tricky one, because it's a sophisticated skill, the idea of line of best fit. I wouldn't for struggling children, I would say if they can get some understand that there is a story to be told in the shape of the results. So if the results are steadily increasing, even if they're not in a dead straight line, because they're unlikely to be, but if they're showing a story of general increasing, then it's not a bad thing to show a curvy line through the dots, or lots of straight lines linking the dots as a preliminary. Right? I know it's not a science skill, apart from some small areas of biological science where people would do this. It's not a skill that we would want to encourage for older students. But to actually think, well, my biggest goal is for the children to see there is a trend, there's a story going in one direction or the other. That for me is the bigger goal, right? The sophistication of drawing a line of best fit is a higher level skill, and you may have to wait for that to come at a later stage. The more important thing is to realise there's a pattern in the results.
Perfect.
Someone's asking me about electricity for kids. I've done quite a bit of writing about electricity teaching for children. In Max Science, there are a couple of big chapters on electricity teaching. You generally need to have equipment which is available at school, simple batteries, connectors, little light bulbs, in order to really teach electricity. It's not a subject I would venture very easily to teach at home. If I were dealing with how to teach electricity for schools, that will be a whole different webinar, and I'm very happy to present that in the future. But it's not a subject, I think, that is going to be done very easily at home, certainly not in a practical sense. What I would say at this stage is that one of the activities I used for teaching electric circuits is to make a human circuit where the electricity was represented by balls of paper passed from hand to hand around a circle of children, and different children wearing different hats with labels on. One might say bulb, one would say battery, one would say switch, and whoever wears the hat with the word switch on controls everyone else and says switch on, switch off, switch on, switch off. As soon as they say switch on, the balls of paper are passed from person to person, and that represents the idea of a continuous circuit. But unless you've got a very, very big family at home, then you won't be able to put children in a circle and do that. But they're the sort of things that I've explained in Max Science. Okay, I'm not sure there are questions I can easily answer here.
I think we will leave it there for now, Bob. I think you've answered quite a lot of the content, so that's fine. In terms of any further questions, do email us and we'll try our best to answer some of those questions if we can, if it's at all possible. But like I said, in the meantime, please do view our webinar recording, which will be live in a few days, and your CPD certificates and the PowerPoint will be available. There may be a delay because we are delivering webinars every week for the next few weeks. So please just be patient with us as much as you can. We would really appreciate it because we have a lot of webinars and a lot of certificates to get through and send out. So if you don't receive it in a week, don't worry, it will be sent at least within 2 weeks, if not. So yeah. We will end it there. Thank you so much to Bob for a great presentation. I think a lot of the attendees found some really useful ideas. And thank you so much to the attendees as well for joining, and stay safe at home. Hopefully we'll be getting back to some sort of normality soon, I hope.
Yes, and hello to all my friends who I've met in the past and all new friends now. I see a whole list of names emerging. Thank you so much for listening, and good luck at home. Good luck with teaching and learning. Enjoy the children in your care, and try some of these experiments yourself if you want, because you'll have fun as well.
Definitely. Take care, everyone, and speak soon. Bye.
Bye-bye.